obviously soil testing as it is, it's a very huge kind of subject. Means we generally in all the universities we have separate courses for that. So I will be touching all the subjects and trying to cover as much as possible, and I will be discussing some points to means that is otherwise ignored in general soil testing practices. So let us start by a brief history of soil testing services in India. As we know that soil testing service began in India in 1955-56. Uh, and the lab in New Delhi, actually where I am posted right now, it is one of those very preliminary labs. Those has been started in back in 1955-56, when this concept of soil testing has been means coined first. Then we can see a growth of this soil testing labs, very high growth in the number of soil testing labs, and presently we have more than 1700 soil testing labs in India, out of which approximately 1500 labs are static labs, like the labs in your university in the ICAR system, and also around 300 mobile labs, which are portable and can be carried from one place to another. So right now we have our country has analyzed annual soil analyzing capacity of around 22.25 million soil samples. So that is no way a small feat, but it needs to be scaled much higher. And currently, as we know, government is focusing much on this soil health, soil testing. They have introduced soil health card, which actually uh, analyzes 12 soil parameters and gives according soil testing recommendations. So obviously this is very important then. And as I was talking about the mobile soil testing labs, these has been becoming very important nowadays, because huge soil analyzing demand is coming, and the total static soil testing labs is not able to meet up that demand. So one that kind of instrument is developed in our lab, on means our division only, division of soils and agriculture chemistry, by Dr. S.C. Datta sir. It's a PUSA soil test fertilizer recommendation meter. It's a programmable, portable, low cost digital equipment, and it can test 12 soil parameter, namely pH, EC, organic carbon, available P, K, sulfur, zinc, boron, iron, manganese, and lime requirement, and also gypsum requirement for the problem soils. And this STFR meter comes with it's means one meter, one shaker, a reagent kit, and it can be also run through battery, through direct electric, and also through solar panel also. So this instrument actually has this all the parameters, and it has around 100 crops data with fit within the instrument, and based on the soil test crop relation equations, it will first ask you, means what is the crop present in that field, and then it's a very simple procedure. Any literate person can do this procedure of soil analysis in this, and then based on that analysis result, it will ask which crop, which region, and what is the yield target, and on the basis of that it can give you direct recommendation of fertilizer. So this is one of a kind of this portable soil testing meter. So very important in now in today's soil analysis scenario of Indian agriculture. So now let us directly move to the topic, that is soil testing. Now soil testing, it's a journey of soil samples from field to labs, then to the recommendation. So there are few major critical steps in soil testing. The most crucial one is sampling, means soil sampling, and the sample processing, because if our sampling is not representative enough of the field, then there is a huge chance of misinterpretation. And then obviously standard methods of analysis should be followed, scientific interpretation of test data should be there, and also formulation of sound recommendation. Now, for the soil sampling, generally where we commit the errors, we fail, sometimes we fail to understand the variability in the soil sampling sites. Uh, so whenever we go for soil sampling, mostly there is two type of soil sampling. One is random sampling and one is grid sampling. Now, grid sampling is generally done for a large area, but for the farmers' fields, farmers' soil samples, we go for generally random sampling. That means from our field, first we have to choose 25 to 30, 30 sampling spots, maybe per acre actually. So means the more the number of sampling spots, more representative sample we can take actually. So sampling spots should be random. In case of this random sampling, they should be they should not fall in the boundary of that fields, or not in a area where there is shades, or maybe not in the uh, area where some manure is being heaped. So to remove those variability, and also for when we go for sampling, first we need to see the soil color, whether it is similar through the area. Maybe one area, some patch is there where some dark kind of patch is there, so we should consider that as a separate area, not in that field. Okay. Then also we should look for the elevation in the field, whether the elevation in the whole field is similar or not. So these things we need to consider when we go for soil sampling. And then there are several soil sampling tools based on the condition of the soil, the moisture, mostly the moisture, the temperature, those kind of things. So there is Khurpi, there is tube auger, there is Kassi, there is post hole auger, there is screw auger. Now, generally for normal soils, the tube auger is the most scientific one that we do, and it's very easy actually to take the samples from 15 centimeter or 30 centimeter depth, that is the root layer. If it's a sample which is having high quantity of water, then postal auger we can use. And say if it is a very dry soil, or we need to go a bit deeper, then we need to go for screw auger. Uh, but for 0 to 15 centimeter, we can take samples from Khurpi also. We first need to make a V-shaped uh, V-shaped hole in that field. Obviously, after uh, clearing the surface of very organic debris, and then we should dig a V up to 15 centimeter and scrap like 2 inches of the sides of that V, inner side of that V, and take that as a sample. Now for each acre, I was telling 15 to 20 number of this sampling spot should be there. Okay. And obviously, if it's a field crop, then we should go for 0 to 15 centimeter. And if it's a perennial crop, which is having very deeper roots, then we have to go for like 1 meter, 0 to 30, 30 to 60, and 60 to 90 centimeter soil sampling is needed. Then after we have taken the samples from a field, and so much of soil samples will be, suppose we are having an area of like 5 acres or maybe, so there will be so much amount of soil sample. Then we need to mix that soil sample first. And how to mix? Obviously we can mix by our hand, spreading that sample on a plastic sheet maybe. So very good mixing is required. Then we have to reduce that bulk soil sample for ease of analysis. So for that we use actually quartering method. In quartering method, we actually spread that sample in a surface and make 4 quadrants out of it. Then discard the opposite quadrants, and then again mix the soil that is present there. So in this process, we are actually decreasing the amount of that initial soil sample to half in each iteration. So at the final, we have to stop when we are getting around 500 gram of samples. So that is our soil sample. Then we should take that soil sample, bring it to lab, and this sample leveling is also very important. Means name of the farmers, name of the client, complete address, sample mark, depth of sample, date of sample, if GPS coordinates are there, brief history of field, and if there is some problems in crops or soil. So those we need to mention there. And regarding that problems in crop in soil, means problem in the crops, when we are going for sampling in a field, maybe we should look for, maybe we should find some spots, some area where uh, farmer will tell that the history of that area is not good. Means in certain patch, crop productivity or crop growth is continuously less for many cropping seasons. So obviously that particular area we had to take as a separate sampling area. Okay, so we need to take two samples from there, one from the rest of the field and another from that problematic area where yields are low. So if we follow all this, then we would be able to take a representative soil sample that we can use for generating recommendation. Now then, soil samples we need to dry, obviously, and dry for drying of samples you need to air dry them in shade. Do not dry in the sunlight, and then you can store them. Now for certain determination like ammonium nitrogen or nitrate nitrogen or some microbial analysis, maybe exchangeable potassium. So those need to be carried out in those fresh samples, not the dried samples. So we need to take care of that because if we dry those samples, then this there will be a chances of error because nitrate will be lost. Some microbes will die if you dry these things. So microbial biomass carbon maybe. So there will be a negative error there. So, and when we are doing some analysis for the wet, means fresh samples, then we separately had to go for moisture determination to determine, means to report those values on the dry soil basis. We should never report our results on the basis of the moist soil weight. Then after for the rest of the samples, after this drying is over, we have to sieve the soils for maximum of the soil parameters. Sieving through 2 millimeter is well enough. Means obviously first we need to grind those samples, then pass them through 2 millimeter, and then those samples we can use for analysis. But if you are doing carbon analysis, right, so for that actually we need a much finer sample. We need to pass those samples through 0.2 millimeter sieve. So for the carbon analysis only, first we have grinded those samples, then we have passed those samples to 2 millimeter sieve. Then whatever soil is passing through that 2 millimeter sieve, then we again take that a small sub sample of that. Again we grind them and pass them through 0.2 millimeter. Now in the first iteration, uh, we will see some of the materials will be left on that sieve, that is more than 0.2 mm. So then again we need to take those samples, again we need to grind them, and then again we need to pass through 0.2 millimeter. We should do this, repeat this process for like 3 to 4 times, uh, trying to make all that subsample to pass through 0.2 millimeter. Now what happens actually, we know soil carbon, that is mostly soil organic matter, that is mainly present in the soil aggregates. Now, soil aggregates are generally having size more than 0.2 millimeter. So, if we just sieve those samples and discard the particles which are on that 0.2 millimeter sieve, then we are basically discarding our carbons only. So, we should not do that. And in case of carbon, why we need 0.2 millimeter sieved samples? Because uh, if we pass them to 0.2 millimeter, that means we are generating very fine particles, which is having a larger surface area. And basically, organic matter analysis, organic carbon analysis, those are oxidation analysis where surface area matters. Means in half an hour, how much soil organic matter is getting in contact with our oxidizing agent. So more the surface area, our reproducibility of our organic matter, organic carbon analysis will be more. So that's why I need finer samples for this. Okay, so uh, actually, I will be talking about every this thing, this methods one by. I will be touching every one of them. So if anyone of you are having any question, you can stop me and ask question. No problem in that. In between, you can stop me. Okay. Now, the first and foremost important soil property is soil reaction, that is soil pH. Now, pH is defined as the negative logarithm of hydrogen ion activity in a solution that we all know basically. pH scale is 0 to 14, less than 7, it is acidic, we say. More than 7, it's alkaline, we say. Uh, Now, this hydrogen ion activity, for that matter, any metal ion activity can be measured electrometrically from the potential of a galvanic cell. So, which actually follows the Nernst equation. Now, what this Nernst equation say? It says that it actually describes the electrode potential which is developed when a metal M is immersed in a solution containing its own ions of activity of a certain activity. So means when this condition is fulfilled, then a certain electrode potential is established. Certain electrode potential is developed. So if we can measure that electrode potential, then we have a chance of measuring that activity of that particular ion. And in this case, this particular ion is hydrogen. Okay. So this is the Nernst equation. We all know E is equal to E naught plus RT by NF log of AM. Here it will be AH. Okay. So uh, in pH meter, we are actually creating one galvanic cell, right, which is having two electrodes. One is a reference electrode. Here we can see this part, a mercury with mercury chloride, that is known as the calomel electrode. Then on the other side of that pH meter, that galvanic cell which we are developing is the glass electrode, which is this one, Ag with AgCl along with standard HCl. So that glass electrode, this glass is very particular kind of glass. This glass is responsive to hydrogen ion concentration. That means if there is a difference in the hydrogen ion concentration in both sides of the glass, then that glass will develop a potential, right? Let me again tell it. In this glass electrode is made of a particular kind of lithium based glass actually. So that will develop a potential if there is a difference in the hydrogen ion concentration in the both sides of that glass membrane. Means inner side of that electrode, glass membrane, and the outer side, there is our test solution. So when this circuit is complete, and we put our this electrodes in a test solution, obviously, which is having a different H plus ion activity as compared to the inner HCl and also the KCl solution there. So then there will be a development of a potential, right? And that potential is what we measure in this through this Nernst equation. And uh, and this is basically those glass electrode and the calomel electrode, which we also known as the reference electrode. And since this now this reference electrode is having a constant potential because the activity of that HCl inside that bulb is constant. So that EMF of this cell can be expressed by this equation, and at a temperature of 25-degree, this equation we can have E is equals to K plus 0.0591 pH. So basically from that electrode potential actually we derive that pH, means that we generally take direct readings from that pH meter. But this is the basic instrumentation, this is the basic chemistry which is happening there in that pH meter. And we all know these things, we will not discuss this. pH can be obviously measured in a saturated soil paste. It can be measured in soil water suspension 1 is to 2 or 1 is to 2.5 suspension. And pH also can be measured in 0.01 molar calcium chloride solution. Now for saturated soil paste, now one thing is important: whenever you are reporting soil pH, then you need to mention which method you have followed for determination of that soil pH. And basically the saturated soil paste method that is used for the problem soils, the saline soils, alkali soils in those cases. For normal soils, agriculture soils, soil water suspension we do 1 is to 2.5 soil water ratio. So there we take soil, add water, stir with glass rods, continuously shake for 5 minutes, and then take the pH readings. And in saturated soil paste, we make a soil which is saturated with water. So we make that paste, right? And then we insert our this pH electrodes in that soil paste and check the pH. Okay,
Excuse me,
so
sir.
yes,
Excuse me, sir.
please.
Sir, I have a question.
Yeah, tell.
Sir, in previous slide you have mentioned about calomel electrode.
Mm-hmm.
Sir, my question is, sir, can you please explain it how it measures the H plus ion differences between glass electrode and the calomel electrode? How it is measured?
Yes, yes, yes. I got your point. See, uh, I will try to explain. Obviously, first, you understood the Nernst equation, how it is measuring actually. Means if we
Yes,
know the
sir.
potential, okay, then we
Yes,
can
sir.
calculate the pH. Yeah. So if we have a standard hydrogen electrode, right? Standard hydrogen electrode, but uh, that is basically non-existent. Means that's a kind of uh, situation, means very standard situation. So if we have that standard one, then we can put that in a solution and it will give us the result. Okay, but we don't have that. We have to measure the that electromotive force or potential of that solution through another electrode which have a very particular reference value, means which have a constant potential, means that we know, right? So that is the calomel electrode. Okay, we know its potential in respect of a standard hydrogen electrode that we already know, right?
Okay, sir.
Means it is, got it?
Yes, sir.
Yeah. And that glass electrode, that is for measuring the potential of that solution. Okay. Now, how we get a potential? We have to complete a electric cell, a galvanic cell, to have any kind of potential. So, in one hand, we have. Let us just see this picture actually. So, in one side, we have the calomel electrode, which is having a constant potential that we already know. In the other side of that cell, we have the glass electrode. And the glass electrode, what is that electrode basically? What is it? It is made of uh, a responsive hydrogen ion responsive glass membrane. Inside it is having a standard HCl, okay, and outside it is having your solution, whatever solution you need to measure the pH of. So H plus concentrations are different uh, in here. I mean, inside the glass and outside the glass membrane. And this glass, as this is a H sensitive glass, that means it is sensitive to H plus concentration difference. If there is a difference, it will develop a potential. And we know the potential of the reference electrode. So basically, potential is not something we can. It is developed of a half a cell, means one electrode. Potential develops for a complete electric cell. So this reference electrode completes that cell, and we know the potential standard, this potential of that calomel electrode in comparison with the standard hydrogen electrode. So from that one, we get the total potential of the system, and how much potential is developed for that hydrogen ion concentration difference. And by putting that value to the Nernst equation, the instrument only calculates our activity of hydrogen ion, and from that activity of hydrogen ion, we have our pH. So that is the basic principle here. And if you need to, means this can't be taught or understood in the period of like 5-10 minutes. uh, this book of analytical chemistry, the Vogel's inorganic chemistry analytical methods, that book you should read if you need to understand very clearly and critically these principles of pH meter, right? You should go through that.
Thank you, sir.
Yeah. And then there is electrical conductivity. It is also similar kind of stuff, you can say. So here also we are we are constructing an electrical cell with a positive electrode and negative electrode. Now, in any solution, if the ion concentration is higher, then the uh, conductance, means conductance of that electrons will be higher. That is the basic principle here. So, and so if there is the movement in those electrons are there, so then again there will be a development of conductance, and again a development of a potential. So that what we are measuring in this case with our electrode. And for every electrode, means for every EC meter, there is a certain value that is called cell constant. That is nothing but is the length of that uh, means it is the separation distance of these two electrodes divided by the surface area of that electrode. So that is basically constant for every EC meter. Our EC meters are obviously calibrated on basis of that only. So that's how we measure electrical conductivity, and we know electrical conductivity measurement is very critical for determining the quality of irrigation water, or maybe characterizing the saline alkali soils, even pH meter also. So these are the two very basic soil parameters that we actually do uh, on the very first day of soil analysis. It's just after collection of the soil. So soil EC measurement is also very easy. We can means we use the potassium chloride solution as that standard. So this zero point zero 0.01 normal KCl actually gives electrical conductivity of 1.41 decimals per meter at 25 degrees centigrade. Again, so that reminds me that temperature is also very critical here for pH and for EC also. So that's why when you will be seeing a pH meter or EC meter, you will be seeing a thermometer, means is also associated nowadays. These are combined actually. So these are associated also, because this nasty question you can say, or that electrical conductivity, it varies with the temperature. But whatever values we report, or whatever classification, characterization, whatever characterization is there of soil, those are mainly based on the values of 25 degrees centigrade ambient temperature. So that thermometer measures the temperature and do the correction in the machine only, and deliver us the values which corresponds to 25 degrees centigrade, 25 degrees centigrade temperature. And EC can also be measured in the soil saturation extract. It will not be paste, it will be extract actually. Means after that saturation paste is made, then we, with the help of a pump and Buckner funnel, we can extract that soil solution from the saturation paste and measure the EC in there. And that is basically done for the problematic soils, the saline soils. And in normal cases, we measure the EC in soil water suspension. So in normal cases, what we do, we first make a soil solution at the ratio of 1:2.5, stir it continuously, means to make a suspension, and we take the pH of that suspension and report it as a soil pH, and after then we give it some time to settle down, and whatever clear extract is remained on top of those soil which has been settled down, we take the EC of that soil extract actually. So that is how we measure the pH and EC. So then the next one, that is, sometimes we say it's the heart of soil fertility, that is soil organic carbon. Obviously this is true, because soil organic matter is the main source of soil organic nutrients, not organ means inherent soil nutrients. Also it is directly related with soil microbial health, biological health, also physical structures. So everything in soil is related to soil organic carbon. So that's why it is very much important. So soil organic carbon, it can be from a soil fertility perspective, uh, the easily oxidizable soil organic carbon, which is Walkley black soil organic carbon, that is more important from a soil fertility perspective. But if we are looking for soil carbon sequestration potential, or rather the physical health or biological health of the soil, then total carbon is also important. Now, total carbon, which we can measure following the Dumas principle of dynamic flash combustion using a CHNS analyzer. You can see the schematic diagram here, and in the corner, this is the instrument actually. So here the samples are weighed. Weight has been taken in like 20-25 milligram. Soil samples are taken in a tin foil. Then we make small tablets of those tin foils and put them in the sampler. You can see the auto sampler over here and also here. So then the sample goes to the combustion chamber where the combustion actually occurs at around 1000 degrees centigrade. And what will happen if this combustion actually occurs? And for that combustion, we use the oxygen as a fuel gas. So after this combustion, carbon is converted to carbon dioxide, hydrogen to water, nitrogen to nitrogen gas or oxides of nitrogen. Means nitrogen, any nitrogen in that soil material will be converting to the nitrogen oxides and sulfur to sulfur oxides, like that. So there this oxidation takes place, and then we have another column of high purity copper. Now this copper, what it does actually, so these gases are now formed in that combustion chamber, and then we have a carrier gas of helium. We can see here a flow of helium is there. This helium then carries this oxides, this gaseous oxides, to the reduction chamber, which is basically overheated copper, overheated high purity copper. So what that copper actually does, that copper takes up the unused oxygen, okay, and also converts the nitrogen oxides to dinitrogen, right, nitrogen gas. So from after passing through that column, now what we get nitrogen, CO2, H2O and SO2. Then a GC column is housed in this portion actually, here you can see. So in that GC column, these gases are categorized based on their retention time on that helium matrix. And then at the outlet of the GC, we have a detector. Means in our case, we have thermal conductivity detector, but we can also have an infrared detector. So there, at different retention times, it will measure those gas outlets, and we will have such chromatograms of different gases at different time intervals. And then the machine itself, it actually integrates those chromatograms, that area of that peak that we can see, and gives us the value in percentage. So this is basically the principle of CHNS analyzer. Okay, so it's a nice instrument, a costly one obviously, and but it gives us very particular results, very correct results, we can say. And but that is for soil carbon sequestration perspectives. Now if we go for the soil fertility perspective, for a fertilizer recommendation point of view, the water black carbon or easily oxidizable soil organic carbon is more relevant. Now why we tell it as an easily oxidizable soil organic carbon? That means here the total amount of soil organic carbon is not oxidized and is not accounted for. Means in case of the Dumas principle, whatever sample we are throwing into that reactor at like 1000 degrees centigrade, it's burning everything. At 1000 degree with oxygen, it's burning everything. So that total CO2 we are getting, so total carbon we are getting. But in case of this one, what we do, we basically treat that soil carbon, soil organic matter, with a oxidizing reagent, that is the dichromate ions. How the dichromate ion is produced? It is produced by mixing of K2Cr2O7 and H2SO4. So in this case, if we react this dichromate ions with carbon, which is having a zero valency in inorganic matter itself, so then this dichromate oxidizes the carbon, and we can see from Cr2O7 2 minus, it is forming Cr3 plus. So it's getting reduced the chromate is getting reduced. Means the oxidation number changes from +6 to +3 in this case, and the carbon is getting oxidized and forming CO2. So in this method, what what is occurring? Uh, in the start of that experiment, we started with one normal K2Cr2O7, say. So a certain normality of K2Cr2O7 is introduced to that system. It oxidizes some of the carbon. So some of that dichromate, some of that chromic acid is, some of that Cr6 plus is getting consumed, and the rest is present there. So that unutilized, unused dichromate, whatever is left in that system, that we measure through back titration with another reducing agent. Here what we use? We use ferrous ammonium sulfate as a reducing agent in the back titration, back redox titration. And from that, we can have the amount of unused Cr2O7. And we already know how much Cr2O7 we actually introduced in the system. So from the difference of both, we can have how much of this chromate ion are being used for oxidation of that carbon. So from there, we can have how much of that carbon is being oxidized in that process. So that is why it is called easily oxidizable soil organic carbon. So and from that reaction, if you see, always remember 1 milliliter of one normal K2Cr2O7 is equals to 0.0036 gram of carbon. So from that, you can actually calculate the other carbon values. Now let us just have a look in the procedure and the reagents. I think you already know this. One normal K2Cr2O7 we need concentrated sulfuric acid, we need 0.5 normal ferrous ammonium sulfate, and we need a diphenyl amine indicator. Means for that titration of K2Cr2 means unused K2Cr2O7 with that ferrous ammonium sulfate. And we need orthophosphoric acid and also sodium fluoride. Now here is one thing we should always remember. If we are having a saline soil, in saline soil, that means it will be having a higher amount of chlorides. If higher amount of chlorides will be there, those chlorides will actually react with some of that potassium dichromate. Means some of the potassium dichromate will be consumed in the reaction with chlorides. So there will be an overestimation of that procedure. Okay. Sorry for that interference actually. So in that case, means if you are having a saline soil which is having high chlorine concentration, then we should add some amount of silver sulfate in that sulfuric acid. So in that case, silver chloride will be forming, precipitation of silver chloride will be there. So it will basically take out all the chloride from the system. So there will be no error. And for that ferrous ammonium sulfate, it is very critical that ferrous ammonium sulfate, what we are having, that color should be a very bright green in color. That color shows it is still ferrous ammonium sulfate. Okay. Now what happens if some ferrous ammonium sulfate is left in the lab for a larger period of time? It will react with the oxygen from the atmosphere, and the ferrous will be oxidized to ferric. Now, if no ferrous is there, how it will actually titrate the potassium dichromate, unused potassium dichromate? So, whenever making that ferrous ammonium sulfate, we need to see the color of that reagent, it should be very bright green. And whenever indenting for those chemicals, we should always go for the small package like 500 gram or something, because if you open the ferroammonium sulfate, then its life is gone actually. Then its shelf life is like 1 month, maximum 1 month. After 1 month, it will be damaged. So that's why you order small quantity, you open it, you do continuous organic carbon analysis for 7-8 days, and just discard it, right? So that way we do this analysis. And again, that ferroammonium sulfate, it should not be stored. In the morning, you prepare ferroammonium sulfate, you standardize it, you use it, and you throw whatever is left in the evening. Because that's ferroammonium sulfate solution also, if left in the lab, it will get oxidized by the oxygen present in the atmosphere. So that point also we need to take care. Now just have a look with the in the procedure. You need to take around 1 gram of soil, add about 10 ml of K2Cr2O7 and 20 ml of H2SO4 in a 500 ml conical flask. Also keep a blank. And now remember, the reaction here starts after addition of sulfuric acid. Now this is pretty simple here, but when we are doing a volume, a bulk of sample analysis, like for any research problem like 40-50 samples a day, then it will be a problem. Then what do? First, you prepare your samples, you add potassium dichromate to all the beakers, and then you start adding H2SO4 one by one. Now you will see, when you add the concentrated H2SO4, there will be a formation of heat, and that heat of digestion actually is what is oxidizing that carbon there. So whenever we add that H2SO4, that means digestion starts, and the method tells us to keep that digestion assembly, we can say that thing, for 30 minutes in the dark. Okay, so time is also important here. So whenever you add H2SO4 in one conical, you note the time, say it's like 2:30 p.m. You write 2:30 p.m. in that conical itself. You move to the next one. Again, you measure your H2SO4, add there. Maybe 1 minute is there. It is 2:31 now. 2:30, 2:32, 2:33, likewise. And now, whenever you see in the your watch, 3 p.m. is there, you add water to the first one. Then again, 3:01 p.m. you add 200 ml distilled water to the second one, and likewise. Now, why we are adding this water here? This water is added just to stop the reaction. Means, so what I'm trying to say, this water like carbon means oxidizable by this potassium dichromate and concentrated H2SO4, and oxidized for the time period of 30 minutes, not more than that. So that time is very important here. Okay. Now say you have taken soil, added this, waited for half an hour, and then you see the color of that assembly. Now see, in this reaction here, the dichromate actually, we all know dichromate is orange in color. Okay, and when it is getting reduced by this soil carbons or organic carbon, it will be producing chromic sulfate, which is having greenish color. So if after 30 minutes you see some tinge of greenish color is there, that means there is no excess of K2Cr2O7 present in the sample. So that then it might be the case that that entire amount of K2Cr2O7 is consumed, and still there is some more organic matter is left. So then there it will be underestimation. So you look for that green color. If it is green color, then you repeat the procedure with taking 0.5 gram of sample, means you reduce the sample. Okay. And if it is orange, very good, then you have excess of dichromate present in the solution, and then you can go for the titration. Then you can add 10 ml of phosphoric acid or and a pinch of sodium fluoride to that solution. Now see, in this total assembly, means in the next step when will be doing the redox titration, back titration, it's a system of means chromium 6 plus, chromium 3 plus, and on the other hand, Fe3 plus and Fe2 plus. Now this redox system has a, what we can say, it has a standard potential of 1.03 volt actually, and the indicator that we are using is diphenylamine. Now for any indicator to show a sharp color change, its formal potential will have to match or be approximately, means around each other, that formal potential of an indicator and the standard potential of the system. Now in this case, the potential, redox potential of the system is around 1.03 volts, whereas the potential, the standard, this formal potential of the indicator here is 0.76 volt. So there is a difference. So sharp color change will not be there. So for that we add orthophosphoric acid or maybe sodium fluoride. So what it does actually, this orthophosphoric acid actually binds with the ferric forms of iron there, and also sodium fluoride also does the same thing. So then it combines with that ortho ferric ions, take those things out from the system. So then that potential of that system will decrease and come around 0.76 volt. So then we can have a sharp color change. Then you add 1 ml of diphenylamine indicator just before the titration. Now this is very important. Again, if you are having like 40 samples, you add diphenylamine to each of the sample and then go for titration. Then by the time you will be getting the last sample, means you will be having very huge errors in your result, because here also the diphenylamine reacts with the your K2Cr2O7 potassium dichromate. So if we keep that dichromate very prolonged in contact with that diphenylamine, so some of the chromate will also be consumed for oxidation of diphenylamine. So then again there will be another means a huge overestimation actually. So to prevent that, add just diphenylamine before the titration, and then do the titration by adding drop by drop the ferrous ammonium sulfate from the burette or maybe use a auto titrator. Color change will be a dark black, inkish dark black to a green color. And again, if the ferrous ammonium sulfate, the titer value is very less, like less than 6 ml, then again you have to repeat the titration with less amount of soil, because that means the ferrous ammonium sulfate requirement is very less. That means the K2Cr2O7, maximum K2Cr2O7 is consumed by the soil organic matter. That means soil is having very high amount of organic matter, so we have to go for less amount of soil. So that is how we do the organic carbon analysis, Walker Black analysis. And as I made mention earlier, in this calculation, first we need to find the strength of the ferrous ammonium sulfate that we are using. That we can actually find from the blank, because we know 10 ml of this K2Cr2O7 we are using of one normal. It's a primary standard, and normality of ferrous ammonium sulfate can be calculated. It is 10 by B. B is the reading for blank. Then we have to find out the volume of unutilized dichromate, right? Which is again we are titrating with the ferrous ammonium sulfate. So we now know the normality of ferrous ammonium sulfate. We know the normality of this one K2Cr2O7, and we know how much of that K2Cr2O7 means. So that's how we can find the volume of that unutilized dichromate. That is Vf is equals to S into 10 by B. Then we know the dichromate which actually oxidizes the carbon, that is Vk, that is equals to 10 minus S into 10 by B. 10 ml of potassium dichromate we have used, and we are measured the unused amount, that is S into 10 by B. So the Vk is equals to 10 into B minus S by B. And obviously 1000 ml of one normal dichromate is equivalent to 3 gram of carbon. So that you should remember, and then just do the calculation and calculate the percentage amount of carbon. So that is about Wachler black carbon, where we use uh, so there that is Wachler black carbon. Now then Chan and his co-workers modified this Wachler and Black method. Wachler and Black, we are only using concentrated H2SO4, that is 36 normal H2SO4 with 10 ml of K2Cr2O7. So ultimately, the normality of that H2SO4 in that Wachler Black method comes around 24 normal. So as I mentioned earlier, that oxidation or that digestion, the heat of that reaction is very important, which is primarily produced by addition of H2SO4 in that mix. So that is proportional to the concentration of H2SO4. So what Chan did, he introduced 5 ml, 10 ml, and 20 ml of concentrated H2SO4 in the same sample in the separate replications. So that correspond to 12, 18, and 24 normal of H2SO4. So from these normalities, we can actually determine the very labile organic carbon, that is the carbon oxidizable under 12 normal H2SO4. Labile organic carbon, the difference between the 18 normal and 12 normal H2SO4 oxidizable carbon. Less labile carbon, there's the difference between the 24 normal, that is the Wachler black carbon, and the 18 normal H2SO4 oxidizable carbon. Then the non-labile organic carbon, there is the difference between the total organic carbon minus the Wachler black carbon. So now different this carbon pools we can determine, and from that we can also calculate carbon management indices, carbon management index, which actually gives us a holistic view of any practice, say for conservation agriculture. We are not conservation agriculture, we are having a forest field, then suddenly we tried cultivating it. So initially, what is the lability of soil organic carbon? That is the Wachler black carbon divided by the non-labile soil organic carbon. Carbon pool index we can calculate. There is the sample total soil organic carbon upon the reference total soil organic carbon. This reference value is the initial total soil organic carbon before starting that practice, means of that initial forest sample. Then lability index of carbon we can measure. There is the lability of SOC in that present condition divided by lability of the reference soil. That means the initial soil. So then CMI we can calculate by this formula CPI into Li into 100. So it actually accounts for the sequestration purpose, the total carbon, and also the lability purpose, which is actually responsible for nutrient release, soil fertility. So to determine the effect of any cultivation practice change on soil organic carbon stability, we can explain that by this CMI. Right? And carbon stocks can be calculated by this formula that you all know actually. So that is about carbon. Now let us just move to the next one. Determination of nitrogen, and I guess I am audible here. I am present and the students are also present. So again, I'm requesting, if any one of you are having any doubts about anything I am saying, you just stop me and ask, because all these things you can have in your book. So let us just focus more on the interaction. So then let us move to the next one, that is the determination of soil nitrogen. Now, in soil, nitrogen is mostly present in the organic form. Say 98% of that soil nitrogen is present in organic form, and very small amount is present as ammonium form and nitrate form. But plant can only take up that ammonium and nitrate form, right? But for from a fertility point of view, this ammonium N and nitrate N can be determined. And if we want to tell something about the C to N ratio or the other parameters regarding the quality of soil organic matter, then we can go for the total nitrogen analysis. The principle is basically same. Now, in case of total nitrogen analysis, be it in soil, plant, or any manure, the principle here, it consists of two steps. One is digestion, another one is distillation. And actually, we should say it's a three-step process: digestion, distillation, and titration. Okay. Now, for digestion, we can see the end digestion unit there. So here we use a digestion mixture, which is a mixture of potassium sulfate and copper sulfate. We add that stuff and H2SO4 and add to our soil organic matter or the plant manure, and then we digest the thing in that digestion unit for around 390-degree temperature, means with a range of 370 to 410 degree centigrade for around 2 hours. The devices are programmable actually. So what happens there? Their H2SO4 is converted to SO2, and also due to that H2SO4 and that temperature, all the organic matter is getting digested. CO2 is evolving out, and nitrogen is getting mineralized, right? Then there is H2SO4 again is getting reduced to SO2, and that SO2 means SO2 developed in that redox reaction, that is again getting reacted with the inorganic N that is been formed there. And then what we are getting the ammonia gas, and that ammonia again reacts with the H2SO4 we added for this digestion to occur. That will give us ammonium sulfate. Now, this ammonium sulfate, or maybe the ammonia that is being formed over here, that will not be lost to atmosphere, because we know ammonia can be lost to atmosphere, can be volatilized when pH is more than 8.5, means in an alkaline pH. But it's a digestion mixture, it's a digestion chamber, or the pH is very less, so there is no chance of volatilization. Okay. So after the digestion over, we take those digestion tubes with the extracts. We should see whether the extracts are clear or not. Means all of that soil organic matter should be digested. We take it to a distillation chamber. We can see here in that distillation chamber, we can see the tube, where the tube can be fit over here, and another one receiver end there. One conical flask should be placed. So then what we try to create an alkaline atmosphere in that tube by adding sodium hydroxide. Means if we are doing for the digested samples, we should use sodium hydroxide, because the digested sample is having a very high amount of H2SO4 very low pH, so we use 40% NOH there. So we try to raise the pH more than 8.5. Now, if it is a more than 8.5 pH, then whatever ammonium sulfate or ammonia is present in that digestion distillation tube, that will be converted to ammonia. Okay, and we are giving in the distillation process. What we are doing, we are also giving heat in that chamber. So in that heat combined with that high alkalinity, the ammonia will be volatilized. Volatilized to where? It will volatilize, go up, and there is a cooling chamber inside the instrument. So in that cooling chamber, those ammonia gases again gets condensed, cooled, and again fall back to this receiver end of the system, that this receiver tube we can see over here. And then that so that means that ammonia will be coming, all the ammonia will come from that distillation tube to that receiver end. So we need a receiver there. So what is our receiver chemical here? We can use boric acid, H3BO3. Now what will happen? That boric acid will absorb all the ammonia and get converted to ammonium borate. So a certain amount of ammonia is getting absorbed there, so, and a certain amount of ammonium borate will be formed. Here also we need to see that we always have to keep excess amount of boric acid in that receiver end. And then we need to measure how much ammonium borate is formed, right? So how we will do that? Now in this process, actually, whenever means boric acid is having an acidic pH, and whenever ammonium borate it is forming after absorption of ammonia, the pH will be higher. So either we can measure that change in pH, and from that we can back calculate, but for a large number of sample it is not possible. So that's why we use a visual method, a titrimetric method, involving an indicator which changes its color with the changes in pH. So there in boric acid we use mixed indicator having pH 4.5. Now boric acid in mixed indicator in boric acid at pH 4.5 is below pH 4.5, it will give you a wine red color, and above pH 4.5 it will give you a greenish color. So that's why we have to maintain that pH at 4.5. That means if a small amount of ammonia is also getting absorbed there, the pH will be over 4.5, maybe 4.51, 4.52. Then green color will be there. Then that after this distillation is over, we need to take that receiver tube, means receiver conical flask with that boric acid there, where ammonium borate is being formed, and then titrate that with standard H2SO4. Maybe for 0.01 normal in case of manure samples. For soil, maybe 0.01 normal, kind of that. So in that titration reaction also, means in the titration process, we can see that ammonium borate will be reacting with the H2SO4, and there will be again formation of boric acid. And when that pH reaches actually 4.5, again the color will be changed to the wine red color. So the starting point of that boric acid is pH 4.5. Ammonium is getting absorbed, pH is increasing, color is changed. And again we are titrating with standard H2SO4 back to that pH 4.5. So we can calculate how much of ammonia has been absorbed. So how much of ammonia are released from that distillation digestion tube. So we know the total nitrogen content. So this is basically the procedure for total nitrogen content estimation. We can see the reagents, dilution mixture, mix indicator, that is a combination of methyl red and bromocresol green in 95% ethyl alcohol, 4% boric acid solution at pH 4.5. So that we need to actually means we have that pH 4.5, fix that pH 4.5 by addition of H2SO4 and this NaOH. And we need to, whenever we are doing nitrogen analysis, we need to see the pH, because that pH will change over time. So just before getting to titration, getting distillation, we should check the pH of that boric acid. If it is somewhere different from 4.5, then we again readjust the pH to 4.5 and go about our process. So then this is the procedure for digestion. Add digestion mixture, add H2SO4, do the digestion at 370 to 410, and always keep your samples for pre-digestion. That is important. And then do the digestion for 1 to 2 hours till clear solution you obtained. Then cool it and go for the distillation. And here the distillation I have already explained, so I will not explain again. And then from now see, from this reaction actually you can see 98 gram of H2SO4 is equivalent to 28 gram of nitrogen. Okay, so 1000 ml 1 normal H2SO4 is equivalent to 14 gram of nitrogen. So T minus B ml, T for titer, B for blank, of N normal nitrogen is equivalent to T minus B into normality, that is of the H2SO4 N into 14 by 1000 gram of nitrogen, and that means into 14 milligram of nitrogen. So that is the basic formula, and based on what nitrogen you are doing from plant sample or maybe from an extract, you can calculate from this equation only. So that is about total soil nitrogen. Then we can go for the mineral nitrogen, right? The mineral nitrogen means how much nitrogen we are having in the mineral form, the ammonium and nitrate form. So to extract that, we need to take 10 gram of soil, add 2 molar of 2 molar KCl, 50 ml 2 molar KCl, and then we need to shake it for 1 hour and obtain a filtrate. Now this we need to do for fresh samples, because otherwise there will be mineralization and loss of nitrate, and also maybe some volatilization can occur. So some denitrification losses may also be there. So then again, after that shaking period is over, we can obtain the clear filtrate, and we take around say 30 ml of that filtrate into that distillation unit and go about our distillation process by using 25 ml of 2% boric acid solution. Now in this assembly, to make that distillation tube alkaline for distillation of ammonia, we use MgO, a pinch of MgO, to change the pH to more than 8.5, to promote the volatilization of ammonia. Now, in this case, we are not adding any acid as earlier in case of the total nitrogen. So only a pinch of MgO, which is a very weak alkali, we can use. It can volatilize actually all of your ammonia, and then we can run the distillation, collect the distillate by absorbing the ammonia, liberated ammonia in 2% boric acid, and then again go for titration. So that is about mineral nitrogen. Now that
Excuse
mineral
me,
nitrogen,
sir.
yes, please.
Sir, in the previous process, we have added 10 ml NaOH for volatilizing the ammonia gas, no, sir?
Yeah.
So can we whatever will be there if we use MgO?
sound is not clear. Can you repeat the question?
Yes, sir. In the previous process, in that macro gel distillation unit, in the previous one, we have added NaOH in place of alkali. Here we have taken
Yes.
MgO. Here we take MgO, no, sir.
Yes. Yes.
Can we take MgO
Why?
or NaOH anyone? Yes, sir.
No. See. Uh, First thing we need to remember that we are measuring. We should not disturb the soil matrix. Okay. Means to recreate the recommendations, give the recommendation. We should recreate the whatever situation is present in the soil that we need to mimic. Now we have to make that thing alkaline. Okay. And here in this case, in that mineral N process given by Ravel 1994, here that MgO is sufficient to make that pH alkaline, means sufficient for volatilization or liberation of ammonia. So we do that. But in the previous, there we actually we had to add H2SO4, concentrated amount of H2SO4 for digesting the samples. So their addition of MgO will not increase your pH to that level where liberation of ammonia will take place. So there we need to add very concentrated amount of alkali just to make that pH. Okay. So that is the main reason. And one more thing actually that I remember now, that this one now this MgO, that MgO needs to be free of carbonates actually. So means that MgO powder, if we keep it in lab after maybe 6 months, 6-7 months, that MgO will react with the carbon dioxide in the air and it will give magnesium carbonate. So if you use that again, so there will be not formation of alkalinity sufficient enough for liberation of ammonia, and we have errors of estimation. So it is better to use fresh MgO, but it is not always means we cannot procure every time. So you can just put that MgO in a oven maybe for some time uh, to just conversion of that magnesium carbonate to again MgO. So that we should use, right? And then this now remember this process. In this process, what we are determining? We are determining the ammonia, right? So we do not know where this ammonia is coming from, but we are only determining ammonia. In case of obviously for the total nitrogen content, there may be, or maybe mostly for plant samples, there is only organic nitrogen that is getting converted to ammonia. So that is the total nitrogen. But when you're doing for mineral nitrogen, there is ammonia and there is nitrate. But if we are measuring by this process, we are measuring only the ammonia, not the nitrate. So when we are doing for mineral nitrogen, then after this process is over, then again you take that distillation tube having that distillate, means that 25 ml of extract of that KCl solution, and you add Devardas alloy. That Devardas alloy is an alloy comprising of copper 50%, aluminum 45%, and zinc 5%. So there, this aluminum and zinc basically they react with the this nitrate ions and also the nitrite ions, and they reduce them to ammonium, right? Then again you run the distillation, do the titration. So for each extract, for each sample extract, you need to run that distillation twice. The first instance without the Devardas alloy, that will give you the value of ammonium nitrogen. The second instance with the Devardas alloy, that will give you the value of nitrate nitrogen. Now that was about the mineral nitrogen. Now mineral nitrogen means a total amount of nitrogen that is present in the soil in the present condition, which can be absorbed by the plant in the present time, very present time. But that is not termed, that cannot be termed as available or mineralizable nitrogen, right? Because available means that amount which is present now and also can be uptaken by plant, by the crop, in its total crop growth period, that is around 3 months, maybe 3 to 4 months for any crop, rice, wheat, or maybe other crops. So that's why this concept came of this mineralizable nitrogen given by Subbiah and Asija in 1956. Here, what do we do? Here, we do not extract the soils with anything. We take a certain amount of soil. We add alkaline potassium permanganate, 0.32% KMNO4, that is an oxidizing agent. And then again we use this means we we run the distillation, no digestion, only distillation. So in that distillation, that nitrogen, that organic matter, it undergoes the alkaline hydrolysis, because we will be also adding sodium hydroxide. Now this is wrongly written here 40% NaOH. We generally use 2.5% NaOH. Okay, remember 2.5% NaOH here. So that 2.5% NaOH again creates an alkaline condition, and since we are having the KMNO4, it again mineralizes some of the organic nitrogen, brings into the solution, and since it's alkaline condition, ammonia will again be liberated and again can be absorbed in boric acid containing mixed indicator, and then we can again titrate that thing with sulfuric acid, and then we can tell this much is mineralizable nitrogen. Now there is obviously a drawback here. In this mineralizable nitrogen also, we are not considering the nitrate portion, but in case of mineral nitrogen, we can consider the nitrate and the ammonium. So these are the nitrogen different methods. This is the most popular one actually, mineralizable nitrogen. Okay, so then let us go to the next methodology, that is for available phosphorus. Now phosphorus chemistry, as we know, it is a bit different in different soil reaction. In case of acidic soils, the phosphorus chemistry, the phosphorus dynamics is mostly governed by the iron aluminum phosphates. And in case of alkaline to calcareous soils or maybe normal soils, that phosphorus chemistry is mainly governed by the calcium phosphates. So obviously extraction mechanism of available phosphorus also is different for different pH soils. The first one is the Olsen method, which we use for the neutral to alkaline soils. Here, what we do, we basically extract the soil with 0.5 molar sodium bicarbonate, pH 8.5, in the presence of dark OG60. Okay, that is charcoal basically. So here we know that mostly the phosphorus are present as calcium phosphate, different varieties of calcium phosphate, dicalcium phosphate, octacalcium phosphate, maybe tricalcium phosphate, apatites maybe. So when we use that sodium bicarbonate here, so it increases the activity of carbonate in that soil solution. Okay, so according to the solubility product principle, when we increase the concentration of carbonate in that solution, right, it will react with the calcium ions, which activity of calcium into activity of carbonate is the solubility product, it's constant, and we are introducing carbonate ions, so activity of carbonate will increase, and in that very logic, to make that solubility product a constant, the calcium ions will be decreased activity of calcium ions. And then if we consider the solubility product of calcium phosphates, the solubility or activity of calcium decreases. So then the activity of phosphorus will be increasing. Or in a very easy language, we can say that those carbonates will be replacing the phosphorus, right? It is not that easier, but we can say it. So calcium carbonates are getting precipitated, and we are having the phosphoric acid, which is soluble. So we are basically extracting that phosphorus from some of the calcium bound phosphorus. So that is the extraction process here. And we can see here we use some of this one, that Darkoji 60 charcoal here. Now, since it's a colorimetric estimation, so if there is a color there, that will interference with our color development and estimation. So that's why you use Darkoji 60, because organic matter, if there will be some organic matter, then it will give us some yellow color, right? And Darkoji 60, it will absorb all the dissolved organic matter, dispersed organic matter, so we will have a colorless extract. Okay, so that is basically the extraction methodology of this Olsen's method. And also uh, some of the aluminum and iron phosphates. Okay, let us tell it in the next slide, maybe. Yes. And then okay, let us just complete the extraction here. And in case of the acidic soils, we use Bray's method. That is Bray and Kurtz, 1945. Here we use a mixture of HCl and ammonium fluoride. Now, this ammonium fluoride, when is reacting with that aluminum and iron phosphate, it will give rise to phosphoric acids and ammonium fluoroferrates and ammonium fluoroaluminates. Okay, those are precipitated. And again, by the same principle, we are getting the H3PO4. By the solubility product principle, we are having H3PO4, means we are extracting the phosphorus from the cell solution. Okay. There is two type of Bray-Kurtz reagent, number one, number two. Number one is 0.03 normal NH4F plus 0.025 normal HCl. And number two is 0.03 normal NH4F plus 0.1 normal HCl. That means it is having a higher concentration of HCl here. So it basically, high concentration of this HCl dissolves more carbonate bound and adsorbed phosphorus, and it includes more apatite phosphorus also. And it extracts both acid soluble and adsorbed phosphorus, where the number one reagent extracts only the adsorbed phosphorus. Okay, so that is about the extraction. Then let us see how this color is being developed. Here the main reagent for now, means we have extracted, we are having H3PO4 phosphate ions in our extracts. Now we need to develop color. So there the main reagent is ammonium molybdate. It is also known as Bray and Dickman and Bray's reagent, 1.5% ammonium molybdate. So that ammonium molybdate, when reacts with HCl, means any acids for that matter, it gives us rise to molybdenic acid. That molybdenic acid H2MO4, when reacts with phosphoric acid H3PO4, it gives rise to phosphomolybdate. Where what happens, the oxygens of that H3PO4, that is being replaced by the molybdate ions MO3O10, and it is forming a yellow colored complex. Means that complex is having a faint yellow color. We tell it as a canary yellow color. So if you can measure, means that intensity of that yellow color is directly proportional to the amount of phosphorus present in the extract. So if you can measure the intensity of that yellow color, we can measure the amount of phosphorus. Now, in case of soil samples, the phosphorus is low, means it's in ppm, maybe some percentage, maybe, but not like the plant samples where very high amount of phosphorus is there. So there, that faint yellow color is very faint, beyond detection actually. Means not beyond detection, but the resolution is not very high between two different phosphorus containing solutions. The resolutions we can't detect. So in that case, what do we use? We use some reductants. We may use stannous chloride. We may use ascorbic acid. We may use amino-naphthosulfuric acid. Those react with that phosphomolybdate, and in that process, some of that MO6 plus is converted to MO3 plus or and MO5 plus. And then due to that reduction, this complex assumes a intense blue color, right? So then we can just measure that blue color, and that intensity of that blue color is proportional to the concentration of phosphorus present in the sample. And so that is basically the principle of this methodology. And let us take a look at the methodology here. The reagents we know: extractant for Olsen's reagent, 0.5 molar 0.5 normal sodium bicarbonate. Braze method, ammonium fluoride and ammonium HCl. Then solution A, there is the ammonium molybdate solution, Dickman and Braze reagent. Ascorbic acid solution. Solution B, standard solution, diluted. And here also we need the dinitrophenol indicator. Okay, so process of Olsen and Bray extraction is very easy. We all know. Now that preparation of standard curve, that we also know. We can take 10 means here. One thing I need to tell that whenever you are developing something, some standard curve or for some estimation, any estimation, whenever you are using the blank, you use that matrix, same matrix for the sample and also for the blanks and also for the standards. Say for Olsen extraction, you use that sodium carbonate as the matrix for the sample extracts and also for the standards. Okay. And you take this 10 ml of sodium carbonate and add your 0 to 25 ml of diluted standard solution in 50 ml 100 flask. And then the dinitrophenol, why we use this, you need to adjust the pH to 5 with 2.5 molar or maybe 5 molar H2SO4 using 2,4-DNP as indicator. Means if we are having a this Olsen reagent, it is having a high pH. pH is adjusted to 8.5. So in that pH, whenever we are adding that thing, that sodium bicarbonate, or maybe the extract, even in case of soil extract, we add 2,4-DNP, and in the alkaline range, that 2,4-DNP will give you a yellow color. Then we need to use 2.5 molar H2SO4. Drop by drop we should add to change that yellow color to colorless. That means we have reached the pH 5. Now why that pH 5 is important? That pH 5 is important because this phosphomolybdate, what it will form, that phosphomolybdate here, that is stable at pH 5, 5.1 rather, pH 5.1, it is very stable, and their other interference from other complexing ions is very less. So that is why we do this. And similar principle for color development in soil extraction. And then you go to your this spectrophotometer and determine the color intensity, absorbance of that blue color at around 760 nanometer. And if you are doing it by the yellow color method, mostly for the plant samples we do that, you can measure that at 420 nanometer. So we know the spectrophotometer basically principles of Bray's principle it follows. So that means any color means any concentration means the incident light, its absorbance is proportional, will be proportional to the concentration present in that solution, the according to that chromophore group. So that we can measure here. And see, in case of blue color method of this P estimation, we can see the color is blue. That means the blue is getting reflected to our eyes, but the maximum absorption is taking place at the complementary color. That means it is absorbing a maximum amount of red color of the total this Vibgeo spectrum. So that's why through the monochromator we actually pass red light, actually means the light of around 660 nanometer. So that's why for this blue color method we use light of 660 for actually stannous chloride one, and for ascorbic acid we use this one 720 nanometer. On the other hand, when we are measuring the yellow color method, when we are using the yellow color method of P estimation, there the color is yellow. That means yellow color is not absorbed. The color is absorption is taking place on the other side, on this area, this violet area basically. So where 420 nanometer is there. So that's what we are talking. So that yellow color method generally we use for plant and manure samples where we are having a very high amount of phosphorus. So there this vanadium molybdenophosphoric acid yellow color method is used, where ammonium molybdate used, and along with means for that color development ammonium metavanadate is also used. That yellow color we know it developed for that means replacement of that oxymolybdenum radicals for the oxygen of phosphate. But since we use the metavanadate also here, so some of the oxyvanadium is also there, which is replacing the phosphates. And when this compound, this is more stable rather than that molybdophosphate compound. So that's how we measure this color by measure the phosphorus content by the yellow colored method. And that vanadate molybdate reagent is known as the Barton's reagent that we can see. And so that is the blue color method, and this is the yellow color method. Yellow color method is applicable in high concentrations of phosphorus, whereas blue color is mainly recommended for the lesser concentration of phosphorus, like in soil. Yellow color is more stable, more simpler, but blue color is less simpler, and stability of the color is also short because we are using a reductant here. So our air is also having oxygen, carbon dioxide, so that may happen here. And interference of other ions is also less in case of yellow color method, which is not that for blue color method. And the color stability is also less for blue than yellow. Okay, so that was about phosphorus. Then we should go to the potassium, available potassium. Here the mostly widely accepted method is by Hanway and Heidel 1952, that is ammonium acetate extractable potassium. So here what the reagent does actually, it replaces the potassium from the exchange sites of soil colloids, and means replaces it by the ammonium ions, and that replaced potassium we can have in our ammonium acetate solution, and that potassium then can be measured in a flame photometer. It's very easy. The ammonium acetate at pH 7 and standard K solution what we need. So, and we know the principle of flame emission spectroscopy also here, means whatever potassium we are having, it actually evaporates, means we keep the extract in the nebulizer and it evaporates this potassium, dissolved potassium, and then it excites those potassium ions basically. And in this excitation, some of the electrons will go to higher energy levels, and then when it again fall back to the ground state of that atom energy level, it will release some of the energy as photons or light spectra. So that is flame emission, and that what we are measuring in here through a detector, and we know how much concentration of that particular ion is there. And in case of a flame photometer, we can measure only basic cations like sodium, potassium, lithium, uh, because they are having a lower excitation energy, and that can only be provided in this flame photometer. Okay. And then there is nitric acid extractable potassium, that is also known as the non-exchangeable potassium, given by Wood and Ritter 1941. Here, what do we measure? We measure the non-exchangeable K, that is in the interlayer spaces of clay minerals. So that cannot be extracted by that ammonium acetate one. So, but that can be extracted by the boiling nitric acid, as that hydronium ions provided by the acid can exchange with the interlayer potassium ions and bring them into the solution, owing to its much greater penetrating power of this hydronium ions compared to the ammonium ions. So, boiling the soil with the nitric acid extract the total amount of potassium, means the non-exchangeable ones and also the exchangeable ones. So we have the total amount of that, and then again we do the exchangeable potassium through ammonium acetate, and by subtracting it from that nitric acid extractable one, we can have the non-exchangeable potassium, which is also very important for determination of fertilizer scheduling for long-term trials, actually, to see the changes in mineralogy basically. Then the next one is next important element is sulfur. Like nitrogen, mostly a huge amount of soil sulfur is present in organic form. But we are mostly, but the plant can only take up the inorganic forms, the mineral forms, and there is basically two reagents that we use for sulfur estimation, means extractant I'm talking about. One is 0.01 molar calcium chloride, 2H2O, and 500 ppm phosphate solution, means prepared from mono calcium phosphate. So both can be used, but more popular is 0.01 molar calcium chloride, 2H2O. Now let me tell you here the extraction mechanism, means calcium or chlorine, it is not having any role in that extraction mechanism. Okay, phosphate can replace some of the sulfur which is absorbed there, so but not chlorine, and calcium also not. So that's why the phosphate solution sometimes give you a higher value of phosphate extraction than this calcium chloride, 0.01 molar calcium chloride. Now this, so why we use this calcium chloride? Even we use this calcium chloride just to obtain clear filtrate, because we know this calcium is a flocculating ions which can cause soil flocculation and forms big size flocculates, and these large flocculates will do not actually passes the filter paper pores, so we can obtain a clear filtrate. But if we do not use this calcium, then we will have a muddy filtrate, because dispersed particle will be there, and those can pass through the filter pores, and we'll have a very muddy filtrate where we cannot develop further, means for determination purpose. So that is the basically the extraction mechanism of this 0.05% or 0.01 molar calcium chloride 2H2O, and it is given by Williams and Stainsburg 1959. And the determination is basically turbidimetric. So here what we do after the extraction, let us first see the water reagents are used. Calcium chloride, then we need a gamma cassia acetic acid solution. Here this preparation of this gamma cassia is very critical. Pure gamma cassia in 400 ml, we had to heat it, again filter it, and means filter, we have to filter it in hot condition. I repeat this step until entire content is filtered. Then we need barium chloride dihydrate solution and the standard solution. And in the process, we take soil, we add our extractant solution, calcium chloride, 1:5 ratio, shake it for 30 minutes, then filter the content through Wattman number 1 filter paper. Take 10 ml of that allocator filter, and then add 1 ml of barium chloride crystal and 1 ml of that 0.5% gum acacia solution. Now here you need to remember that first we are adding barium chloride solution. So when barium chloride powder, sorry, not solution, that barium chloride when react with this sulfate present in that extract, it will form barium sulfate, which is a white precipitate. And then we add the 0.5% gum acacia solution. Now this gum acacia here, it prevents those precipitate to fall down due to gravity. It keeps those precipitate as a suspension in the solution. And shake the content then to mix properly and take a reading on 420 nanometer. Okay, but here we are not measuring the absorption of light here. What here we are measuring the turbidity, means light is getting light is falling on that, means here we are not having a clear solution. Here we are having a turbid solution, so light is falling on it and it is getting refracted, reflected even. So that what we are measuring. So this is basically turbidity, turbidimetry. Now this can be also done with a nephelometer, where the detector will be placed at a 90-degree angle with the light beam. Otherwise, simple spectrophotometer can measure the transmitted light here and can tell you how much sulfur is there, because obviously the amount of that transmitted light is inversely proportional to the amount of barium sulfate which is forming, which is also clearly proportional with the sulfate concentration in the extract. Now this sulfate is only the mineral sulfate present in the soil, so sometimes it does not very good well correlate with the plant uptake. So then heat soluble sulfur or sulfur availability index are developed for giving that some recommendation with inclusion of organic forms also. The next one is the available boron in soil. Here what we have hot water extraction, Berger and Trow 1939. Then hot calcium chloride also we have. Now see here the extraction potential in case extraction mechanism in case of available boron also nothing to do with calcium chloride. It is the heat energy, right? Means you are providing that soil some heat energy so that oscillation actually changes, and through that heat energy whatever boron is present in the soil solution, means as a borate anion or H3BO3 freely available in the solution, that will obviously come, and along with it, due to that boiling, that heat energy, the amount whatever amount maybe come from the uh, boron that is absorbed or present on the exchange surfaces maybe, and maybe some organically bound boron maybe. So all that thing, the extraction mechanism is external heat here, nothing else. And obviously the calcium chloride is only we use for having means color free organic matter, and also a clear filtrate. For that we are using this. Uh, uh, now mm, now there is another method we can use, 0.05 molar mannitol, 0.01 molar calcium we can use for higher pH soils, pH 8.5. And now for acidic soils, a better methodology is by using 0.1 molar salicylic acid as an extractant that we can use. Now let us just so those were the extraction, and for the estimation purpose we can use the azomethane H. This azomethane H can uh, form complex with the H3BO3 that is getting extracted by that method and give us a yellow color. and it forms a stable complex at pH 5.1, and maximum absorbance occurs at around 420 nanometer, and this is rapid reliable technique and generally followed everywhere. So hot calcium chloride method, these are the reagents we can see. Now there is one important reagent, that is the buffer solution. Now this is known as buffer masking solution. Remember the name, buffer masking solution. Here 250 gram of ammonium acetate along with 15 gram of disodium EDTA in 400 ml of distilled water along with 125 ml of glacial acetic acid. So this is being used obviously for maintaining that pH at 5.1. Then azomethane H here, 0.45 gram of azomethane H in 100 ml of ascorbic acid solution. Now azomethane H is also a reagent which cannot be used if stored, and azomethane H is very costly. Azomethane H is very costly, around 25,000 for like 10-15 grams. So we should use it judiciously. We should prepare the azomethane H in the morning, see how much samples we have, and consume the whole azomethane H by the evening. Do not store the azomethane H, other it will not give you any result if you store it prepared azomethane H for more than 2 days. So do not do that. Let us just go through the procedure here. 10 grams means 1:2 soil is to this calcium chloride solution ratio. Now here since heating is involved there, so after taking those soil and calcium chloride, you take the weight of that total conical flask. Then heat the content for exactly 10 minutes, because in the process it is written as 10 minutes after starting of the boiling, not after starting of the heating. You should see when the boiling is getting started, wait for 10 minutes and then remove your conical flask from there. Then you just cool it and again weigh the conical flask, right? And there obviously, since boiling is there, some loss of water vapor will be there, obviously, and that loss of water vapor you have to make up with addition of distilled water, double distilled water. This we do for means for keeping the soil is to solution ratio constant. It will help in calculation part. Otherwise, we do not know how much water is there. Means originally 150 ml means 20 ml is used water, means the total matrix there. Then you filter it through water number 42. Then take 1 ml of allicate in 10 ml polypropylene tube. Add 2 ml of buffer solution. Mix thoroughly. Add 2 ml azomethane H and again mix thoroughly. Develop the color and read that color in a spectrophotometer. Now here 2-3 things are there. That is since it's boron, and all our borosil glasswares is also having means they are made from borosilicates, so they are having boron in them. So never ever do this boron analysis in a freshly glasswares. So that will give you some error maybe. So what you can do, you can have your glasswares and treat with some hot acid bath, means keep it in a hot acid bath for like 2-3 days, then remove it and again keep it in a hot alkali bath, then again in a hot acid bath, and then properly wash it. So in that way, whatever boron that might be present in that borosilicate one that could have compromised your accuracy of estimation will be already removed. So that is how we do this boron in available boron in the neutral to alkaline soils. And then yeah, one more thing which is important here, that is this buffer masking solution. Now see, this methodology also develops a yellow color, and since we are having soil heating it with water or calcium chloride, There may be some organic matter removal, and that will also give yellow color. That may be interfering with your this all the process. So you can add charcoal. Obviously, it will remove your organic matter, but that dissolved organic matter is also a source of available boron. So if you remove that organic matter, so you will be losing some boron also. In case of phosphorus, the amount of phosphorus in soil is much higher as compared to the amount of boron. It is in very less ppms actually. So there we can use the charcoal, but here we cannot use charcoal. Okay, but after you taking the aliquot, you will be seeing maybe some yellow color is present there because of dissolved organic matter. Then you add 2 ml of your buffer solution, buffer masking solution, and mix thoroughly. Now, after addition of this 2 ml buffer solution, you will see the pH is raised to 5.5 and the color, whatever is present, yellow, that is totally removed. If it is removed, then only use azomethane solution for color development. If not, then then that means your soil is having a very high amount of organic matter. So there you have to add charcoal. And if you are adding charcoal, add in the blanks, add in the standard, and also in the samples. Okay. So that is about boron in this neutral to alkaline soils. In case of acidic soils, uh, rest reagents are the same. Only the extractant we use is 0.1 molar salicylic acid uh, dissolved in triethanol amine, yeah, and make the volume up to 1 liter. Okay. And here the buffer solution is a bit different. In earlier case, we are using 15 gram of disodium EDTA, but here we are using 30 gram of disodium EDTA because we are doing it in a acidic soil, and there might be presence of some iron oxides actually, which also impart some of that yellowish color. So to remove that one, we use this an extra amount of disodium EDTA here, extra 15 gram. So here no heating is there. Here only 1:2 ratio. You take the soil and solution and shake it for 1 hour, and then rest of the process is same. Then I guess the soil testing, the last one, another important, that is the cationic micronutrients. In this case, what we use the DTPA, that is diethylene triamine pentacetic acid, given by Lindsay and Norman in 1978. So this reagent composition is 0.05 molar DTPA plus 0.1 molar TEA and 0.01 molar calcium chloride at pH 7.3. So what it does, this DTPA actually acts as a chelating agent, and during this extraction, it reduces, means it makes chelates with these different micronutrient cations. It reduces their free activity in the soil solution due to this formation of soluble metal chelate complexes. So there will be a reduction in the iron concentration in the solution, in soil solution. Then in response to this depletion, some metal ions will come from the solid phase, maybe absorbed in organic matter, maybe clay surfaces. So that will again give us not only the current soil solution micronutrients, but the micronutrient concentration which can be uptaken by the plant in the total crop growth period. And such depletion in the activity of metal ions in solution closely mimics with the reduction in activity of metal ions in solution due to plant uptake. So this is a very good method for extraction of this cationic micronutrients. So we use 1:2 ratio of soil is to ETPA solution, 2 hour shaking for 25 degrees centigrade. Filtered through hot number 42, and then measure the concentration through any ICP or atomic absorption spectrophotometer. Now here also some things are very important. We need to see this 2 hour is very important. This has been seen that with a crop growth, this 2 hours is means the 2 hours extraction is directly has a very high correlation with the plant uptake and plant yield behaviors. And 25-degree for micronutrients, mostly for means in our case in Delhi actually, here the temperature varies huge from the winter to summer, maybe from 10-15 degrees in winter to like 40-45 degrees in summer. So there we need to have an environmental checker, because this micronutrient extraction efficiency is hugely different. Means for zinc, for example, 10% extraction increases if we increase a 10-degree temperature here. So for that, always extraction should be done in an environmental shaker at 25 degrees centigrade. Now just a few couple of things. Here also we use this triethanolamine to maintain that pH at 7.3. And also this TEA, when present in the soil, it gives rise some HTA ions, right? And that again removes some calcium ions from the exchangeable surfaces in the soil. And also we are giving it calcium chloride, so more of the calcium ions we are giving. Now why is that? Because see, this method is basically developed for the calcareous soils of USA. So just to prevent the DTPA to chelate all the calcium carbonate bound micronutrient fractions, which is otherwise unavailable to the plant, we use this one. It increases the calcium concentration in the soil solution, so it prevents the calcium chlorides from solubilizing. Okay, so whatever calcium carbonate bound or calcium carbonate co-precipitated ions are there, those will not come into the solution. So we'll be not having those overestimation, but due to its high chelation capacity, it mimics the plant behavior, and it can actually take out the uh, micronutrients from the solid phases, which otherwise plant can also take up during its total crop growth period. So that is for available micronutrients, and there we can measure this after extraction. We can measure this by atomic absorption spectroscopy, where we have some hollow cathode lamps in the machine structure, which actually are made of the same element that we are going to measure. Say we are going for zinc, so a zinc hollow cathode lamp will be there. So what happens actually? There is a it's a hollow cathode, means the cathode is hollow, but the anode is here solid. And we when we pass electricity toward this, so it will generate some electrons, and those electrons actually sputter, means actually hit the hollow cathode, and those get excited, those ions in that hollow cathode. So excited is go to the excited state and then again come back to the ground zero state, and that energy is uh, converted to a light, means characteristic light of that particular ion. And in this chamber, means that this lamp actually, here the nebulizer is there. Here the samples are aspirated, and samples again are in the heat source. It has been uh, distributed to the ground atomic state, but not excited. So this here, they can actually absorb the light which is coming from the hollow cathode lamp, and that amount of absorption is obviously proportional to the amount of ion present in there in the extraction medium, the filtrate. So then it that light goes to the photomultiplier tube, the monochromator, and we can have the reading. So that is why it is absorption spectroscopy, and the flame photometer there, that is a emission spectroscopy. Okay, so and this can also be done through ICP-MS, which is also an example of flame emission spectroscopy, right? So here what we do, we are actually making a plasma here, this inductively coupled plasma. So here a quartz torch is there, and there on that quartz torch, some copper coil is basically there, and we flow a current through that copper foil, and those copper foils are highly, what you can say, highly conductive. So for that, uh, it develops actually some charge fields here, some magnetic fields, and through that thing, means through that quartz torch, we flow the argon plasma. Now that argon, when in that magnetic field, it gives rise to, basically we give it argon gas, and when in that magnetic field, that argon gas actually dissociates into plasma. Now plasma means when the atom is also will be present, and some ionic forms also will be present, and that give rise to a very high temperature of 7,000 degrees centigrade. So see, for the materials which are can be excited in the low energy state, flame photometer, sorry, there if no energy is needed, chromophore group is present, so there that can be measured in spectrophotometer. Then if some energy is needed for excitation with small amount of energy, so those can be easily estimated in flame photometer, where we are basically using a very low temperature, only flame. Then absorption spectroscopy comes, where we are measuring the micronutrient cations. But here also, the elements like silver, or maybe obviously only cations can be deal with absorption spectroscopy, but silicon, boron, this cannot be, because silver may be, because they are having a very high energy of excitation. So for that, we are needing a very high amount of temperature, which can be only provided through ICP-MS. So that is how we can do our micronutrient extraction. So that completes our the topic, the first topic that I have given to, that is the soil testing, the normal soil testing method. So if anything, any questions are in there, so you can ask. And I will request our coordinators for another 30 minutes actually, because this topic is very large. It took an excess of time. So may I continue for another maybe 20 to 30 minutes?
Yes, sir. Sir, if you want, sir, you continue, sir. No problem.
Okay. Means
But
if
sir,
all
there
the
is
students are interested.
only few students in the sir lecture, sir. So we continue another day in the Saturday or Sunday, sir, with some leisure
Okay, no
time.
problem. We can stop here over here also.
Yes,
So
yes.
as you wish.
Yes, sir. Yes. Actually, sir, there is a session of the university actually closed. The time to close the university is 6 o'clock, sir. So many of the students leave their labs and go to the
Okay.
hostel, sir. So,
Okay.
so
So let us not means have this futile exercise.
yes, yes,
So I have completed all the soil testing processes, I guess. And if you can tell me another any half an hour slot anywhere,
yes, yes,
maybe
sir. Yes,
tomorrow,
sir.
maybe day after tomorrow, anyone, I will complete it. No
Yes,
problem.
sir, we will make
Definitely.
that provision, no problem.
Okay. Okay.
So,
Thank you, sir. Then,
may I audible?
Yes, sir. Yes, sir. You are audible,
yes,
sir.
sir, you are audible, sir.
Yes, yes. Thank you very much, Dr. Abhilde sir, for giving a very
Thank
nice
you, sir.
information regarding all the aspects of soil, because the analysis is a very important part in your research work, and also all the principles regarding the nitrogen, phosphorus, potassium, and all these analysis is very important. You have given very nice information regarding all the principles, procedures, calculations and everything for the student. Definitely that information will help them for their analytical work as well as for the preparation of all these ARA, GRF, SRF and all these studies and also for their interview purposes. Thank you very much, sir, on behalf of the post director, on behalf of the faculty, and on behalf of all the participants. I am very much thankful for you for sparing your valuable time for giving this lecture. Thank you. Thank you very much, sir.
Thank you, sir. Thank you.
Thank you,
Thank you
sir.
for inviting me.
Yes,
Thank
yes.
you, sir.
Very, very nice and very informative lecture, sir. We will spare one separate slot again for the remaining parts, sir. Definitely.
Yeah, yes, sir. Only half an hour, not more
Yes,
than
yes,
that.
definitely, sir.
Okay. Thank you, sir.
Okay. Okay.
Thank you so much, sir.
Yeah. Thank you.
Thank you,
Much
sir.
more.
Okay. Okay. Thank you.
Thank you,
Any
sir.
questions if you
Thank
have,
you behalf of all the
we'll discuss in
students,
the
sir.
next class.
Okay, sir. We will
Yeah. Thank
continue
you.
in the
Thank
next
you.
session.
Yeah. Thank you. Thank you.
Alka, please in the meeting. You are now host. अरे यार क्या किसको होस्ट बना के गई ये सोई हुई होगी हेलो अलका